My name is 𝘎𝘮𝘯𝘬, a professor at 𝘎𝘮𝘯𝘧 University in Cleveland, Georgia. I'm going to talk about how it is that organisms got from the ark out to the various corners of the world, at least a hypothesis that I think will help in our understanding of that period of time. The story really starts for me in following Mount St. Helens, the eruption at Mount St. Helens. At the end of the eruption, in Spirit Lake to the north of the mountain, there were about 1 million logs lying on top of the water, floating on top of the water of Spirit Lake. Over the years, those many of those logs have become waterlogged, float down to the bottom of or sink down to the bottom of the lake. But even today, now more than 40 years after the event, there are still hundreds of thousands of logs floating on Spirit Lake, still not having become waterlogged and falling down to the bottom. A study by Steve Austin, done over a period of a decade and a half or so of time following the eruption, was that different species of trees would in fact float for different amounts of time. So that by the time about 12 to 14 years had elapsed since the eruption, the only logs left are one species. But that species, he estimated, had a half-time flotation. In other words, about half of them would sink and fall down to the bottom of the lake in about 75 years, which means probably for centuries. The logs on Spirit Lake, or many of the logs on Spirit Lake, will still be floating. That got me to thinking about what would happen in a global flood that in fact overwhelmed not just a single forest in a given valley, but actually overwhelmed the forests of the world in a global flood. It's a number of those trees are probably going to get destroyed and buried immediately, but it's got to be that billions upon billions of trees are going to be floating by the end of that initial destruction period on the surface waters of the flood. And if these logs can float for centuries following Mount St. Helens eruption, then I would think those logs could be there for centuries following the eruption of Mount St. Helens. Those logs would then be in huge log mats that probably would be blown around the oceans in cycles, the same way winds today blow oceans currents around the oceans. I think those log mats were probably being blown around the oceans in probably very much the same places that modern currents are being blown around the oceans. And with those log mats, probably there were other things floating with it, other vegetation material, not just pure logs, but other debris, including fresh water, probably floated on ocean water. We see in the present that sometimes fresh water has a difficult time mixing with salt water and can persist for decades following a period of mixing and stay separate. Fresh water, of course, would float on the salt water, which is denser, and so it could well be that these log mats are floating in lakes, if you wish, of fresh water, and going round and around in the oceans of the world for centuries following the flood. And it's very possible then, it seemed to me, that animals could sort of hitch a ride. They'd go out to the log mat and float their way around the ocean and cross huge bodies of water when those organisms normally wouldn't be able to do such a thing as that. So if that rafting model is true, if it really was true that there were floating mats of vegetation, floating log mats that organisms could make their way across the ocean on, then perhaps that could explain some things that are kind of weird in the present world that are otherwise cannot be explained. For example, we have terrestrial organisms on either side of ocean bodies that are only found at those two locations on opposite sides of the body, and not in places where it's even. So the organisms don't seem to be moving around the ocean body and getting to the other location, perhaps prevented by a different climate. But we have very strange distribution, what we call disjunct populations of the same organism on opposite sides of oceans, that maybe this would explain. Now, it would seem that it would explain it if the two disjunct populations are separated by a modern ocean current that runs from one to the other. So let's look at a few examples. There are a number of disjunct populations called austral disjunct populations that are actually between Australia and South America, sometimes also with pieces of Antarctica. Here's an example of a beech tree, Nothofagus, that is found only, and the only place in the world this genus is found, is in eastern Australia, western South America, and a projection in Antarctica. And there is a southern equatorial current that runs from South America to Australia that such a rafting model might explain. We find some lichens in the same position. We have a plant genus Tetrachondra, which is found in New Zealand and South America, that could be explained by this hypothesis. There's a freshwater shrimp that is found, can't survive in the saltwater in between, but it's found again in southern South America, southern Australia. Freshwater snail genus, Glaciodorbus, that is also in the same locations. We have the caddisfly genera Ecnomina and Astratonoides, that is found in southern Australia, southern South America, and in fact all the way up to Central America. But again, the distribution across the ocean could be explained by this rafting hypothesis. We have another one, some waratahs are on both sides. This is the chironomid flies. There's a bunch of them in New Zealand, a bunch of them in South America, and in Australia. They're closely related to one another. It very well could be they're separated in those locations by the same mechanism. Another plant genus in the family Rosaceae is found not just in Australia, South America, but also in southern Africa. And of course, there is a circum-Antarctic current that can take them to those locations. So it could well be that the modern genera here, modern genus of Acina, was distributed after the flood in this manner, in this floating vegetation manner. Also, another one in the Asteraceae family, freshwater crustacean, has a similar distribution across all the southern continents, both east and west Australia, southernmost Africa, and southernmost South America. Chironomids, an insect species, insect genus. These are actually two families that are distributed only, the only place in the world they're known are these southern continents. We move to a different set, equatorial, Amphi-Pacific disjoint populations. There's a number of organisms that are found in the tropical regions on opposite sides of the Pacific Ocean. And of course, the Pacific Ocean is huge, so you aren't going to be swimming this puppy. And we don't have any evidence of the organisms having made it to the other side of the ocean in any other way. We don't find them up here. And of course, in order to do so, you're going from a tropical environment through a cold environment to finally get back down to a tropical. So there are probably various good reasons why they did not do it by land. They, in fact, would have been rafting could be the explanation. And again, there are currents that move from the New World to the Old World in the Pacific, crossing the Pacific, and all of the locations where they're found are very close to or in the midst of those modern currents. plant genus Paratetia, and another plant genus in the Ericaceae. We got some lizards that are found in the Indonesian and in the Indonesian islands in Southeast Asia and in Central America. Again, rafting could explain how they could be found in just those places alone. A little further north, we have the snail genus Cecina, which is found on two sides of the Pacific. And again, in order to cross a land bridge to make it from one place to another, they have to go through some pretty cold places, which probably would prevent them from being able to do so. Likewise, there's a stonefly species that is found in a similar area. Also in the North Atlantic as well as the North Pacific, there's some marine algal species that are found in in surface waters. Here it's a kind of a different situation where it's difficult to explain how you can get from one ocean to the other, but in a flood with these algae floating in flood waters, before the flood waters dropped and separated the two populations, it could explain how they end up in these two locations in the present. Going back to equatorial regions or subequatorial regions, now focusing on the Atlantic Ocean, we have a number of populations that are found, disjunct populations between South America and Africa. Here's an example, freshwater fish example. The cichlids are very famous fish family, often found in aquaria, that are found in South America and Africa and no place else, with hundreds of miles of salt water in between that they cannot tolerate. So floating again in freshwater, swimming in freshwater lakes after the flood that would eventually get mixed in with salt water and not be usable after a couple of centuries following the flood, could explain how they ended up in the two continents soon after the flood. We've got another example from among the insects, midge. We've got some snails, some mussels here, some freshwater mussels that are found on either side. There are many examples between Africa and South America. There's some lizards on both sides. Going north, in the North Atlantic, we have a North Atlantic, the famous Gulf Stream that connects, at least by current, connects North America with Europe. Got a freshwater snail that's on both sides of the Atlantic, a stonefly genus on both sides, a salamander family that's found on both sides of the ocean there. Some freshwater fishes again from both locations. Underground freshwater fishes in caves in both locations. Very difficult to explain crossing an ocean from freshwater cave fish. Freshwater clams on each side of the North Atlantic. Then some marine organisms that live on the shoreline. They might be attached to floating logs as they go across the ocean and get deposited on the other side. Again, another marine algal species we referred to before. Some plant species on either side of the Atlantic. Freshwater shrimp or shrimp-like species on both sides. And moving up into the polar ocean, there's a polar ocean current that could move anything through all of those islands to the north. So we've got some plants up there and some moving back down to the tropics and moving into the next ocean, into the Indian Ocean. We have connections between Africa and India and Southeast Asia and Indonesia. And there are good currents that connect those locations all the way into Australia. There's another example from some freshwater snails, freshwater mussels, a snake family that's found in those multiple continents there. Some birds. They think that maybe there's, even though some birds can actually fly very long distances, there are others that stay within a continent and don't cross bodies of water, and their distribution could be explained by this rafting mechanism. Rhinos, about rhinoceroses in 2 locations, probably transported, if they're doing it on rafts, they're probably small rhinoceroses or young ones. The dwarf elephants that ultimately produce, and later after the flood, produce the larger elephants that are found in Africa and Southeast Asia. Some lemurs, both positions, some pangolins in both positions. We have a number of examples of disjunct populations that could actually be explained by this rafting model. Now, at the same time, there are a few, not very many, but there are some disjunct populations that don't seem to be explainable by this rafting mechanism. We have, for example, one caddisfly genus which is found in eastern North America and easternmost Asia. Obviously, there's not an ocean in between here, that at least the currents that would be taking them from one place to another. There's actually several easternmost U.S. and China connections. Here's a salamander family that's found in both places. In Magnolia, the genus Magnolia, that's very popular in this southeast. Catalpa, sassafras, all of these genera are only found in southeastern United States and sometimes into the Caribbean, and then in China and surrounding areas. And it's with the simple rafting model I've talked about, this is not easily explained. There is a possibility that I'm working on at this point that there was actually a seaway that ran through here immediately after the flood that got closed. And it could be, as I work on this, I might find that there's good reason to believe there was a current that would have actually connected easternmost North America with Central Asia and even Eastern Asia. So that's research to be pursued in the future. Paddlefish, one of my favorite fishes, paddlefish in the Mississippi. There's another, the same genus is found in China. There's some crustaceans that are found in Japan and Europe. It again would be difficult in the simple rafting model, but perhaps would be explained by a modified rafting model that I'm working on in the future. Frog family in both locations, China and Europe. Freshwater crustacean example here of a family found in India and Japan. Freshwater crustacean family. Now this is a little bit weird in a different sense, although this one might be explainable. By this rafting principle, we've got Australia and South Africa that are connected by a current, and then there is a current that comes off of Australia, comes up into the northern part of the Indian Ocean. It might explain the distribution of these freshwater crustaceans in India and the southern continents. But we have some other southern and northern continent disjunct populations that are a little more challenging to explain. There aren't very many of these examples, but there are a few. So if the rafting model is true, it would explain most of the world's disjunct populations, which is somewhat encouraging. All but a few. There are a few that are challenging yet. Another way to test the model, or another expectation of the model, is if the rafting model is true, it places where the current comes onto the land, if it is actually picking up organisms from the other continent and dumping them onto that continent there, then those would be places where it would appear that that organism appears on the continent coming out of the sea, kind of a gate into that continent, and then spreads from there. It's interesting, before the time of Charles Darwin, biogeography was very popular. There was a lot of work done in biogeography in the 19th century. All of that completely dropped. People stopped doing it with Darwin's theory. Even though Darwin's theory didn't explain the biogeographic patterns, perhaps that's why it was dropped. But anyway, there's some wonderful biogeographic work done in the 19th century that was simply forgotten all the way up until the present. One is a work that argued that there seemed to be places on continents where new organisms would enter the continent and spread from there. And these were called biogeographic gates. 𝘎𝘯𝘶 is the individual who made that argument in the 19th century. He identified these gates. There's a gate in Australia. It looked like, for the Australian organisms, that many of them somehow came into Australia at this gate location and then spread from there to the rest of Australia. On South America, the gate that 𝘎𝘯𝘶 discovered or hypothesized is on the western coast of South America, and the organisms spread from there to South America. On Africa, the gate is in southern Africa, moving up and spreading into the rest of Africa. Another one into Asia is up here in the Arabian Peninsula, and another one is in Western Australia. What's kind of interesting here is that currents are coming into gate C, would actually explain why this would be a gate. Currents are approaching D, explaining why that's a gate. There's a current approaching B that would explain that gate. And there's even a current that is approaching A to explain that one. And although that current comes up the whole side of South America, there is another current that feeds E. So it very well could be that this floating mat hypothesis, this rafting hypothesis, would explain why 𝘎𝘯𝘶 found biogeographic gates around the world. So it could well be that the rafting model explains these gates. Also, those same landing sites, or any landing site, would be a place where you would expect more unique organisms to be located there than anywhere else on that continent that is being received. These would be areas of high endemism, unique to that particular area. And Candolle, both of these are French biogeographers, very famous biogeographers of the 19th century. These are all the locations that Candolle identified as areas of high endemism around the world, and many of them correspond to, in fact, places where currents come in to or connect with the continents. And so I think it's very possible that this model will ultimately explain Candolle's areas of high endemism. So rafting theory, I would suggest, explains some biogeographic patterns that have been either ignored for a couple of centuries, or at the very least, they haven't been explained in any way by any other model that I'm aware of. There needs to be a resurrection of this biogeographic study to confirm the observations made in the 19th century, or perhaps extend them, and then to test this against this rafting model. Now, if the rafting model is true, there are some other predictions that I would make, that I have made, Here's an example of 16 such predictions that could be tested in the fossil record and in the present fauna and flora of the world. This is just a preliminary investigation, and so I've made predictions that can be tested in future research, and I think there's good reason to believe that this could be a very powerful and exciting explanation of a number of biogeographic patterns that have not heretofore had an explanation. In addition to that, providing an explanation for how organisms could disperse quickly after the flood.